Hi everyone, my name is Sharon Azulay. I'm the CEO of Plexistor. I'll give you a brief overview of our product and the problem and the solution that we are proposing. So let's take a look at what's inside Plexistor. What we're doing in order to achieve this ultra-low latency, this near memory speed experience, and at the same time the capacity and the data enterprise and the enterprise grade features is converging memory and storage together. We are creating a new paradigm in storage where you can actually decide how you can experience the storage. You can experience the storage as a storage device or as a memory device. It's your choice. The way for us to do that is to create a multi-tier architecture where the primary tier, the working tier, is based on byte addressable storage. And the reason I'm emphasizing byte addressable storage is because it can be traditional DRAM or it can be non-volatile DIMMs. Okay, going forward, what we have today, non-volatile DIMMs comes from Micron, from Gigatech, from SK Hynix. Those are pretty much DRAM backed by flash with some kind of a supercap attached to that. In the case of a power failure, the data is copied from the DRAM to the flash part. In the case of a power recovery, it goes back from the flash to the DRAM. It gives us last transaction safety. It gives us the ability to maintain the byte addressability capability and at the same time gain the persistency of storage. This is why NVDIMM technology is so interesting. Going forward, Intel has announced the 3D cross point. That's definitely a target for us. We believe 3D cross point is definitely going to change the way we are building data centers. And in order to better utilize and bring 3D cross point to the mass market, we need something that will take this byte addressable technology and expose it in a way that traditional applications, existing applications, can consume.
Okay, so, but you're selling a software product, right?
Absolutely.
As an end user customer, I can't really buy NVDIMMs from Viking or Micron or Netlist because they require BIOS support.
Absolutely.
And so is your go-to-market OEM so that you can package this into an appliance from a vendor whose motherboard has the appropriate BIOS support for some specific NVDIMM? Because I like rolling my own, but that's one step beyond where I'm comfortable.
I don't, by the way. It's a lot of things to do. But you're absolutely right. NVDIMM is a new technology. In a sense, it's not new technology. It's been here for quite a while. But to bring it to mass market, Intel had to make changes to the BIOS to support it. By the way, the servers that you have today in your data center do not support non-volatile DIMMs. Okay? They do not support it. And I'm not even talking about 3D cross point. That's not just a new system board. That's a new CPU to deal with. The way for us to go to market is, first of all, this is why we are approaching the big data market. They're actually counting on the fact that storage is ephemeral, is volatile by definition. This is why it's so easy for us to propose a solution not based on NVDIMM. But in the case of MySQL, you're not going to lose your last transaction. You're going to say, listen, this is a big no-no. I'm not going to lose my database. How can I deploy a non-volatile DIMM technology? And the way for us to do that is to work with system integrators and VARs. So what we are providing is just a license, and you, the VAR, will build a system based on a HCL that we're going to provide you, and you're going to ship the systems. Assuming you are a system integrator, of course.
I think that's a heavy lift.
Yeah, I'm still a little bit confused by that. So it's software.
Yes.
And you will work with VARs and
Well,
systems integrators who will buy the appropriate server with the right BIOS to use NVDIMMs.
Correct.
Okay. Right.
Only for certain use cases, absolutely.
Right.
Well, this is storage field day, so we tend to think about persistence.
Absolutely.
Yeah. Because part of it, I got the impression that it was an abstraction layer that would allow you to use things other than NVDIMM. Is that the case?
Correct, it does.
Okay. We just haven't got to
Well,
that.
he does have the yellow and red on the
Yeah,
slide.
I know.
but
So we just haven't got there yet. That's okay.
Before
Okay.
we poke at that.
Good, good.
So the way this entire hierarchy of devices, and before I'm going to go to the flash and the disk, what Plexistor is doing is exposing this memory, either non-volatile or volatile, doesn't really matter, byte addressable storage. The application is through a POSIX API. So from your experience, you're experiencing a file system. You don't care. You're seeing a traditional file system, a POSIX file system, and you can run your traditional applications that rely on the POSIX API to access traditional storage.
Okay, to be entirely antagonistic, I had a RAM disk on my PC XT in 1982.
Sure.
That took RAM and presented it as block storage, and then I ran, well, FAT, because it was the only file system there was back then. What's the big difference here?
My impression is that it's the inverse of that. It's taking block stuff and turning it into bytes.
So it's doing both.
You wouldn't
it's
get
doing both.
consistency in that.
I'll actually cover that later.
What, in a RAM?
So,
Okay.
Yeah. Let's let him answer. Sorry.
So this is actually going
Well
to be
said, however.
this is actually going to be covered in the technical presentation, and trust me, Amit is going to go over those nasty details. But just as in a nutshell,
Bring your dog again.
but just as in a nutshell, there is a big difference between RAM disk and what Plexistor is doing, aside being a multi-tier versus a single tier, which is easy, performance-wise, and of course maintaining persistency. The fact that the underlying storage eventually is DRAM, RAMFS or RAM disk took a lot of discounts or considerations about the memory. And it's not really maintaining persistency in the case of a power failure. You can't really recover in the case of a power failure from the memory back to the RAM disk. So there is a difference. I'll let Amit cover that in details during his technical presentation.
So it combines the RAM and the flash into a single usable entity,
Address space.
which also maintains persistence after a reboot.
Exactly, exactly. So what we're doing is creating some kind, and I'll try to go, I'll explain to that. I'll try to explain it in a very high level. We're creating a huge virtual address space. Part of it is implemented by memory. Part of it is implemented by the SSD. And again, it's exposed as a virtual address space, the file system on top. The only thing the file system knows what to do is just byte addressable storage. It doesn't know how to deal with blocks, okay? So everything needs to be converted eventually to an address space. This is why our solution is so unique, and this is actually why we can deliver such a unique performance. You will see later the difference in the data flow compared to traditional storage and the Plexistor data flow. But just to get back to the stack, so what we're doing is converging the first layer, the non-volatile, the flash, and even the third tier into a single namespace. So from your perspective, you don't really know, you don't really care. You're getting a file system. We are managing the tiering up and the tiering down of data between the primary tier, the memory part, and the traditional SSD device, giving you a very simple experience where you're just seeing it as a storage device. You don't really care what's inside. Aside to that, our proprietary tier, the third tier, can be a traditional HDD. It can also be an Amazon S3. The difference between the first, the second, and the third tiers is that between the first and the second, we are paging pages out, in and out. We are working at the page resolution. Between the second and the third tier, we are actually tearing up and tearing down the complete file. Okay, so the use of the third tier is really for data that you're not planning to use or willing to accept the fact that to retrieve a data from the third tier is going to take a long time.
But now, can I do that programmatically?
You can tell the system what to do. You can identify or tell her this file needs to be pinned, quote unquote, in the primary tier, or this file is cold enough, I don't mind it to push it down.
That's not really what I was thinking of.
Okay.
You know, in the Hadoop environment, you know, I'm going to run MapReduce jobs against data sets, but Monday it's a different data set than it is Wednesday.
Correct.
You know, Tuesday, is there an API for me to say, this set of files that you moved out to disk, I'm going to need tomorrow?
Yeah, so basically POSIX allows you, it's within that interface. I mean, we haven't invented that, right? It allows you to do a fadvise and madvise. So you can basically say will need, don't need, and provide other hints as well to the access.
So one of the things we try to do is to adhere to the POSIX API, trying not to invent something new as far as the API. We want to be as compatible as possible with existing applications. And lucky for us, Advise is there to assist us doing exactly that. So the system, as I said, can scale up. You can add more capacity on each tier. It can also scale out. One thing that needs to be understood to be cleared about the scaling out capability, when we are scaling out, we cannot scale performance. Okay? We can scale compute, we can scale maybe capacity, but we cannot scale performance. We've reached the limit of performance on a single machine, and Amit will go over the performance numbers, and you will see why this is really the limit. We reached to memory performance. Going to the network will add network latency. So if the data is outside of the realm of the physical machine, you will incur extra latency because of the network. We are also providing a proactive optimization engine that sits aside the application, the main file system, continuously monitoring the file system, making sure it's up to highly tuned, correctly tuned. And one of the things we've noticed with customers is over time, the system is drifting, not the file system itself, but rather the workload that the user is employing on the system, and continuously monitoring and giving away or returning tuning instructions is an attempt to maintain the performance of the system over time. As far as HA, we are providing, and this is an upcoming feature, not available in this release, we are providing an HA capability, a mirroring capability. In the case of a DRAM implementation, you can actually create a secondary system, and the system is going to be copied page by page. And Amit will go over that in his presentation. So we talked about the POSIX API. We are also providing a memory API, which is implemented again by the POSIX API itself. It's called memory map or mmap. And what mmap is doing is taking a certain file, mapping it to the virtual address space of the machine. And from your perspective, what you got is a huge memory chunk. It doesn't care how this memory chunk is implemented. When Plexistor is getting this request, it's implementing it part on the physical memory, it can be DRAM or NVDIMM, and part of it on SSD, and paging it correctly, so you're maintaining memory performance efficiency. Any questions? We also support existing infrastructure, and in this case, we are supporting NVMe over Fabric, once available. We are supporting traditional all-flash arrays through iSCSI. Any block device that can provide the right performance will meet the system requirements. And in this case, in this drawing, we can actually see that the all-flash array is acting as the secondary tier for Plexistor. Okay? Again, the primary tier is going to be the memory part. The secondary tier, in this case, is the all-flash array. This way we can
explain the link between the two. When some data comes in, a write, for example, that's always goes to the memory layer, I assume. Is it then destaged over time, and how does it know which blocks to put in which layer?
So it's not cache. So once data is written to the primary tier, it's almost by definition do not exist in the secondary tier and vice versa. This is the difference between tiering and storage tiers and caching. The only reason for us to tier down data is temperature. So no one is using the page or the file or whatever. And I need space. Okay, this is really the only trigger for me to take data from the primary tier and push it down to the SSD. So the traffic, quote unquote, between the primary tier and the secondary tier is based on the usage of the system. Okay.
Is that based on real time? Is it sort of looking at the last 20 minutes? I mean, how does it work out what's hot and what's not?
So I'll let Amit explain that in his technical presentation. We've got certain algorithms that determines the usage pattern and trying also to predict what's going to happen. Okay, it's all in a purpose to maintain near memory speed. So how does it really impact application, this performance that we are talking about? I didn't actually mention numbers, so I'll give you just a quick look into the performance of the file system. The benchmark we are running is a benchmark. It's the traditional benchmark for file systems. And we've been able to show on a very, actually a moderated system, in this case it's 2650 with 32 gigabyte of DRAM and 32 gigabyte of NVDIMM, which can be replaced by traditional DRAM again if you are in an ephemeral configuration. We've been able to achieve 5 million I/O operations per second, 4K random read-write. It's completely symmetric, by the way, and it's not surprising, I guess, it's memory. And 3 microsecond latency on a fully loaded system. Okay? When I'm saying 3 microseconds, this is how long it takes us to acknowledge the application level write. Okay? That's not the underlying infrastructure below. This is actually what the application is experiencing. This is the throughput and the latency that the application is experiencing. And the way it's being translated to applications, what I did was picking on two use cases. One of them is Cassandra, the other one is MongoDB. We've got benchmarks for other applications as well. But I think the interesting point here is that we can show that, let's take a look at Cassandra. In the Cassandra use case, the moment you're reaching twice the memory size, okay, the working set reached twice the size of the memory size, meaning we are spilling over to storage. Okay, this is where Plexistor kicking in. We've been able to provide, I'm sorry, that's not the right button. We've been able to provide 17,000 Cassandra ops per second. That's not IOPS, that's queries per second in compared to 2,000 ops per second using XFS. Okay, the numbers are actually going to be worse for ZFS and probably the same range for ext4. And you can actually see that not just the sheer performance, but also the rate of degradation in performance is actually much better with Plexistor, where using Cassandra with the traditional configuration, at 5 times the size of memory, what you're getting is pretty much zero performance. One thing that needs to be noted, the requirement was that transaction shouldn't take more than 10 milliseconds, meaning that in this case, what we're getting is more than 10 millisecond latency. This is why it's at 0. We're not getting any transaction that's being executed in less than 10 milliseconds.
And that's the Cloud Speed SSD backing store?
In this case, the Cassandra is done on Amazon i2 for extra large. That's an Amazon deployment.
Okay.
Okay.
But what's
inside? What kind of SSD inside?
You've added a RAM layer.
True.
And so, I don't know i2 extra large offhand. Is that a flash?
It's a flash-based system.
Okay.
Yes, absolutely. And the reason I'm saying it's twice the size of memory is to show that we are actually spilling over.
No, that part I got. It's the hitting the 10 millisecond. If it was a disk-based backing store,
that wouldn't
be
fair.
really easy.
Absolutely. I'm not that. So it's based on SSD. i2 for extra large is I think it's
actually 4 SSDs, LVM.
That's all I that's all I needed to know.
And we really try to make sure that we are giving it a fair fight, and we provided the same kind of resources, exactly the same with and without.
You understand that's not always true.
Comparing that to MongoDB, the case for MongoDB is actually even more interesting. We can see that in the case of when you're hitting the 2.7x memory size, when the working set is 2.7 times the memory size, you can see a dramatic drop-off in performance to 20,000, and from that on, it's pretty much going south. With Plexistor, we've been able to maintain 60,000 ops per second at that point. What it means eventually is that we are capable of providing you a buffer for the drifting in performance. Once your working set is increasing just a bit beyond the memory size, in most systems, you're going to get a dramatic drop-off in performance. We can make it smoother. It doesn't mean that Plexistor can provide always the performance. There is a limit even for Plexistor, but especially going twice, 3 times, 4 times the performance, the capacity, we can definitely handle that. Quickly about the GotoMarket strategy. I think that's the last slide. We are targeting the on-premise, the cloud, and the ISVs. We've started with the cloud. That's actually the easiest. We have an AMI deployed in Amazon. You can install it in seconds. It's a ready-made instance of Plexistor, and you can enjoy the benefits. We are also working with ISVs, in this case, open source vendors that wants to create an extra value to their commercial editions, and through that capture more market and generate more revenue from existing install base. This is something we're seeing with open source guys. It's very difficult for them to create a differentiation between the commercial edition and the open source edition. We can add an extra value for them to do exactly that. And of course, the on-premise guys that wants to build high-performance converged infrastructure, either by buying their own equipment or going through system integrators or VARs. to get a ready-made system. Customer profile, customers that have a high interest rate, dynamic workloads, and are very sensitive to user experience, and of course, like everyone else, CapEx, OpEx sensitive, and running applications. We're actually focusing on applications like Redis, MongoDB, Hadoop, Cassandra, and other I/O and memory-intensive applications.